Welcome to Homework 16, Problems 4.5, 1, 3, and 6. Draw the shear force and bending moment diagrams for a simple beam supporting two equal concentrated loads. Repeat if the left-hand load is upward and the right-hand load is downward. In order to solve for a shear force diagram, I have to have every force. If you look at this and you say these are all the forces, yeah, those are all the applied forces, but that doesn't tell us of the reactive forces. I have a reactive force at A and B, and they are both pointed up, and they are of magnitude P. There's two ways I could have known that. Either I did a sum of the moments at A and B, and then a sum of forces to find them, or I could have said my P's are equidistant away, and they are also equal magnitude, and therefore my A and B must also be the magnitudes of my point loads. And they're also in the same direction, which helps as well. Now anyways, moving on to the shear force diagram. In order to plot shear forces, all you have to do is follow the loads. So at point A, and just for simplicity here, I'm going to say the downward P, the left one, is point C, and the right one is point D. Okay. So at point A, I have an upward magnitude P load. So I'm going to go up for my shear diagram by magnitude P, and then nothing's happening until we reach C, in which case it goes down, bringing us back to 0 for our shear, and then I can do that same thing for the remainder of my beam. And thus I get my shear diagram, and it is that simple. For my bending moment, same deal, except now I'm integrating it. So think, if I want to integrate from point A to point C, I'm going a distance of little a, and I have a slope of P, and the slope is a positive P because we're integrating, so it's saying that P is the slope of my line, or in other words, I just have, it's a constant slope too, so it's just going to be a straight line. It's going to be a straight line from having 0 moment to some non-zero moment, and we know that because we have some positive area here, and we can just solve for that. It's A times P, so we can go up to a height of A times P linearly, and then we're integrating 0, so it's a flat line, and then back down. Something to note for shear and bending moment diagrams is you will always start and end at 0. Sometimes you might think that you're not starting or ending at 0 because you might have a point load or a point moment that instantly takes you away or towards 0, but you are, because if we look at our shear, which is the one that doesn't seem to start and end at 0, that's, if you include the point loads there, it is in fact starting and ending at 0. If you don't start and end at 0, it's because you did the problem wrong, so you just need to look at it and try to figure out where you made a mistake. For the next problem, we have our upward load at C. So now I need to solve for my reactions again. They will change. Once I do my sum of moments, this is the answers I'll get. Now, notice if you didn't have your arrows in the orientation that I have them, you will have gotten different magnitudes. You might have gotten P times 1 minus 2A over L, say if your arrow is pointing downward at location A, or something similar than that, depending on how you notate things. So the difference between that and this is, although I have an upward arrow, look at my magnitude here. It's actually going to be negative because A, if you look at the graph, I have 2 A's on the top plus some unknown distance. So 2A plus C equals a total length of L. So in other words, if I look at this 2A over L minus 1 in my parentheses here, 2A is less than L, so in other words, I have a fraction that's less than 1 minus 1, so I have P multiplied by some negative number. So that's what's happening here. So whenever I'm plotting it, my arrow is upwards, but I have a negative magnitude here, and so I'm going up by a negative amount, and so I end up drawing it downwards, and then I can follow everything else kind of simply because it's not super complicated. Now if that racked your brains and you didn't like that you're going the opposite direction of your arrow, when you come to this, you can kind of just keep in mind what I just did, or you can just rotate your arrow upside down. Let's say that I had my arrow pointing up and I come up with I solve this symbolically because there's no numbers available to me, but I have to think, okay, well this is negative, so I can just turn my arrow upside down and then switch my parentheses here. I would have had 1 minus 2a over L. Whatever you need to do to make sure you don't make the mistake, make sure you do that. Doesn't really matter. And then my P is going to bring me above the 0 axis, or above it's going to pass 0. And know this because 2a over L minus 1 is a negative value between 0 and 1, and then I have that multiplied by P, and P is one of them, so it's going to be a little bit above, depending on how big P is. Now we need to solve for the moments. Again, we're going to integrate. So for the first part, I have a negative amount that I'm integrating, so my slope has to go downward, and I can just... Oh, actually, I forgot. I was going to tell you how to find these magnitudes first. So again, we found that the downward magnitude was this P amount, which was 2a over L minus 1. And then you say, okay, well, how do we know what our magnitude is once we pass the line? So because we're just adding our P, bingo, that you're done. I mean, if this wasn't symbolic, you could get a numerical value for it. Since it is symbolic, you could simplify it. I haven't simplified it for you, but you could say, oh, okay, well, we have a minus 1 in here, so we can add a P, and I just get 2a over L times P, and that's the height of it. And now, yes, now we're moving on to moments. So we have our downward slope, and it's going to be of a slope of P times 2a over L minus 1, and that's because that's the height there. And then once we reach this point, now we have our new height, so we solved that symbolically. We said P multiplied by 2a over L was the height between C and D, and so that's going to be our new slope, and then we can follow it down towards the bottom, and we get our new moment. And you can again say, okay, well, how do I know what is the actual magnitude of my maximum and minimums here? So I'm going to solve for the bottom one first. Because our slope was P times 2a over L minus 1, you multiply it by our A, and that's it, that's the end. It's because it's a rectangle. And then the other one is equal, so it's going to be the same thing. But let's say we want to make it a little bit harder on ourselves and want to solve it if we only know the preceding information and we didn't know that it was equidistant and all this convenient stuff for us. So we start out with our previous value of P times 2a over L minus 1 times A. And now we're going to add the fact that we have our new slope of, we have a P amount, right? So if I look at my diagram on the left, I went up by a P, and my P is going across a distance of L minus 2a, right? So that's the new height of my diagram here. And you just add them together, simplify it, and that's going to be your height. And then, of course, it ends up at 0. Draw the shear force and bending moment diagram for the cantilever beam carrying a uniform load of intensity Q over half of its length. Alright, so now we have to deal with distributed loads. I am going to redraw it because I want to put a point load here, just so it makes it easier to find my reactive force and my reactive moment. However, whenever I am doing my diagrams, I cannot include my point load because that's made up. It's not actually there. I only did that to make math easy. So I'm going to follow my true reaction, go over because nothing's happening, and then slant down because we have a distributed load. And then I can graph that here, and my magnitude at the top will be the magnitude that it went up at the beginning, and then it's just a slant, so I'm not going to label that part. As for my moment, it is the integral of my shear. We're going to start by going down by my magnitude, and then we have that flat portion, so it's just a straight line. So I have I simplified my magnitude here. So before, when I solved for my reactive, I left it as my point load times the distance, which was 3/4 L. However, it's just simplified right here. Anyways, we go up by our P magnitude, Q over L halves times this distance, L halves, once we've reached that distance of L halves. And that's how we get our new magnitude there. But because there's this distributed load here, we have this gross curve, and luckily we're not exactly making an equation for it. You could if you want to, because if, for example, for the simple part, for the straight line, we could have said, okay, our P is Q L halves times X instead of L halves, the second L halves there. We could have put an X there, and that would have been true. The magnitude of our moment would have been negative 3Q times L halves over 8 plus Q L halves X. And that would have given us our moment magnitude from the point 0 to L halves. And then we could do the same thing for L halves to L, where we have what we have right here. So negative 3Q blah 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 plus Q L halves plus, and then our Q times the distance that you've had it go, so X minus L halves, times the moment portion of it, so that centroid, so X minus L halves over 2. And that would give you the function of the moment there. However, we don't really care about that. We're just graphing right now. Don't worry about it. The point is, you have this quadratic portion. And if you don't want to graph it out, which is what 99.9% of us are going to not want to do, just notice that our shear is larger on the left side than on the right side, which means the slope is going to be higher on that part, which is why I have it kind of going off to 0 almost on the right side. And that's pretty much a good way to know, oh, this is how it's going to be plotted. The simple beam AB shown in the figure is subjected to a concentrated load P and a clockwise couple M sub 1 equals PL over 3 acting at the third points. Draw the shear force and bending moment diagram for this beam. So, kind of gross, but it won't be too bad. If I recall my sums are equal to 0, then I can find my reactive forces on A and B. So I can label them now. I can now make my shear diagram. That wasn't too difficult. My moment, however, this is where it gets trippy. So we know how to do the straight lines. No big deal. Pretty much what you need to know is clockwise on whenever you're doing your moment diagram, whenever it's on your beam clockwise and you're going from the left, that is going up. That is positive. Counterclockwise is negative. And you can look at the previous problem as well, where we had our cantilever beam and we had it going counterclockwise and we went downward. That's pretty much the only tricky new thing about this. So we plot it and we can find our magnitudes here with the same methods that we've done in every previous problem. Alright, shared moment diagrams. I'm going to go into more detail than you need to know. However, if this helps you at all, then, because I know for some people this is a hard topic, I'm just going to go into more detail than what you'll actually see on, say, homework or test. So our sum of forces in moments is 0, where shear is the same thing basically as our force, except it's in the beam. So I'm going to look at my cantilever beam from that problem we did earlier, and we're going to kind of look at it in detail. So if I choose some arbitrary location and cut it there, then I know that my shear will be the same as my reactive force because nothing's happening. And then my moment, though, will not be the same as my moment because it has shifted over a little bit. So my moment was QL times 3/4 L, but I need to subtract the portion that is removed because of the distance that's now changed. And that's what I get, is that equation. Then if I do the same thing for some new distance out, still shear's the same, and we can draw that to continue until we reach our distributed load. And then we have the same equation for my moment, except that I'm changing x1 to x2. And it will continue in that path until we reach our distributed load. Now, if I'm going to choose some spot in my distributed load, I need to start integrating when I'm solving for my shear as well. And due to the fact that shear is a function of our forces, and our force is distributed, we have Q distribution load over some distance from 0 to x1. And notice here my x1 is not being defined from my origin, I'm defining it from my L halves distance. So if it was all the way from the origin, then I would just have it from L halves to x1. Doesn't matter, same deal. It's because our Q isn't taking place over there anyways. There's different ways you can denote it. That's what I'm trying to say here. And you could also, if you did go from L halves to L halves plus x or x1, you would even have to include in your equation that your Q is subtracting that L halves distance, since it doesn't actually have a load there. Anyways, in my opinion, how I have it denoted right here is possibly the simplest way to denote it. And then for my moment diagram, so what I have written right here is the same thing as what I verbally said when we were on this problem. However, I believe I said x1 minus L halves. It doesn't really matter since we're squaring it, so whichever side would be negative it's going to be positive now. And we can do the same thing for some other distance, and all we're doing is changing x1 to x2. It's just an integral, and due to the fact that we have a square on the bottom for our moment, it gives us this pretty curved line. And if you want to know how to derive it, just know that you don't need to know how to derive this equation that I've shown for this class. However, I'm sure you could go see a TA and hopefully they know how to do this. Or you can just look at what I have here and see if you can kind of conceptually understand it yourself. But this is what's happening. Your moments and your shears are functions of some position, and so you want to be able to find what that magnitude is at any position. And whether you use integrals or you can simplify it with general shapes, it is fine and it's good. Hopefully this was helpful. Good luck on your homework and have a good day.